Professor Bialis here. In this video, we're going to be covering sections 5.1 and 5.5. I combined those two sections because they're all talking about the exponent rules. The 5.5 also takes on scientific notation, but that's not a very big topic, so that's why I like to combine them as one idea. Okay, so what we're going to be doing is just, again, going through these rules. We're going to kind of do an example, set the rule, do an example, set the rule, and at the very end we'll tie it all together. Okay, so first thing I want to do before we actually get into the rules themselves is talk about the parts of an exponential statement. So let's say I have something like that. Okay, just so we're all on the same page. This little number up top, that's your exponent. This number here that it's attached to is your base. I'm going to be referencing that base a lot in this discussion, so I want to make sure you guys understand what that is. Okay, we have to read these very literally. So if I have something like this versus something like this, okay, I've talked about this in a previous video, but again, I just want to make sure we're on the same page. Here we have that exponent of 2, here we have the exponent of 2. The difference is the base here is 3. That is the only thing that 2 is attached to. This base is a negative 3. In this case, that would be a negative 3 times 3, or a negative 9. And here we would have a negative 3 times a negative 3, or a positive 9. Okay? So a very slight difference, but a big difference in terms of the outcome. Okay? So let's look at some of these exponent rules now. So let's start off with something like this. Let's say we have x cubed times x squared. Okay? Now what I want you to notice there is that we have the same base being multiplied. Okay? What do we do with those exponents when we want to simplify these two parts together? Okay? So if you know, great. If not though, I want you to remember, if you are ever in doubt, expand it out. Okay? What do I mean by that? X cubed times x squared. What is that really saying? X cubed is x times x times x. X squared is x times x. And then we were multiplying all that together in the first place. So what are we really multiplying in this case? We're multiplying 5 x's. So all this is an x to the 5th. So what did we do with those exponents? Whenever we have, here are your rules, whenever we have a base times the same base, we would simply add the exponents. Okay, now with this, that's not a big deal, but what if I gave you x to the 32nd times x to the 51st? I don't want to have to expand that out. Okay, but we can still use that expansion as an example. Let's say you have this on a test. Don't write out 32 x's and 51 x's and then count them. If you go back to this, if you can recognize that these are pretty much the exact same problem, taking something like this and then whittling it down to more manageable numbers, you can expand it and say, oh yeah, I add here, so I'm going to add here. Don't be afraid to do that. Okay? So 32 plus 51 is x to the 83rd. That's it. Okay? Now, how about something like this? Let's say we have x squared cubed. So this is a power to a power. Now, notice it's not that, okay, where it's just a 2 cubed as an exponent. This is the x squared, and then that whole thing is then being cubed. Here, this would just be x to the 8th. Okay, you're just taking 2 cubed. There's no real rule happening there. But up here, how do we work this? Okay, now again, if you're not sure, expand this out to see what's really happening. We have an x squared times x squared times x squared. We got x squared 3 different times. So then we would take these and add those up. 2 plus 2 plus 2 is x to the 6th. What could we have done with the original exponents without having to expand them out? We could have just taken 2 times 3. So if we have a base raised to an exponent, and then that whole thing raised to another exponent, simply multiply the exponents. Nothing more than that. Okay? How about something like this? Okay, now our base is actually a product of multiple terms. Okay, it's still one base, but we have a product. So what we're able to do here is essentially apply that exponent onto both. So this turns into x to the fourth, y to the fourth. Now, why is that the case? Because if we were to expand this out, xy, 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 xy. All of this is one big product. And if we just multiply those like bases together, we get x to the fourth and then y to the fourth. Again, we can skip that expansion if we just know the 4 goes down to both of them. Okay? So another rule could be a times b to the m, let's say, and then a to the m, b to the m. What I'm doing here is modeling the rule, as opposed to saying when I have a base that has 2 terms being multiplied, or 3 or 4, I would take the exponent and I would put it on each part of the term. Instead of saying that, I'm just modeling it with these variables. Okay? Now, before we go on to another rule, let's kind of pull some of these together. Let's say we have x squared y cubed and that whole thing to the 5th. Okay? Now, remember, the rule we just had tells us to put that 5th power onto both of those. Okay? Now, when we do that, we have x squared to the 5th and y cubed to the 5th. So now we have a different type of problem which requires the use of a different rule. The different rule here is when we have a power to a power like this, we multiply them. So what this turns out to be is x to the 10th, y to the 15th. Okay? As you're doing these problems, don't feel like you have to do this intermediate step. If you can just multiply and write down that, that's fine with me. Okay, just be careful when you're going through it. If you do show this and you make a silly multiplication mistake, then I and yourself can see, oh, I knew what I was doing, I just made that mistake. So the more work you show, the easier it is for me and you, more importantly you, to catch your mistake. Okay, but don't feel like you have to show every single in-between step. Okay? A very similar rule would be when we have a base that is a quotient. Okay? Same thing here. We are going to take that exponent and apply it to both the top and the bottom. Okay? Let's look at an example. Let's say we have x squared y to the 3rd over a to the 4th b, and then that whole thing raised to the 5th power. Okay? Now that last rule tells us to take this 5th and put it on the top, put it on the bottom. But when we're putting that 5th power to that whole denominator and whole numerator, we would then put it into each of those pieces as well. So really what's happening is we're taking that outside exponent and putting it on every piece that's inside that quantity. Okay, so what we have is an x to the 10th, y to the 15th, and then an a to the 20th, b to the 5th. And that 5th is because, remember, there's a 1 understood to be there. Whenever there's no exponent, it's understood to be 1. So 1 times 5 gives us that 5th. Okay? And there you go. Notice all we did was multiply a bunch of things. Nothing more than that. We just had to know that that's what needs to be done. Okay? All of these rules, we're adding, we're multiplying. That's it. We just need to know what to do and when. Okay? So take your time. Again, good bookkeeping. You got to keep track of everything so you don't get messy. And it's real easy. Okay? Now, let's expand on this idea of dividing. This division rule we have here isn't really a division rule because the numerator and denominator were different. What if they're the same? Let's say we have something like that, okay? Now again, when in doubt, expand it out. What do I mean? X to the fifth is 5x's being multiplied. X to the third, 3x is being multiplied, okay? Now remember, whenever you have something, or a factor, not just something, but a factor on the top and the same factor on the bottom, all you need to do is cross them out because an x over an x divides out to a 1. So what happens with this, gone, gone, gone. They wipe each other out 1 to 1, okay? Now what's left is 2 x's in that numerator. So all we're going to write is an x squared, okay? You could have x squared over 1, but we typically don't write that 1 down. We just write the x squared. Now what's a quicker way we could have done that? We didn't have to write out all those x's. Notice the 5 and the 3. All we really needed to do was take the numerator exponent minus the denominator exponent. And that would give us the result we're looking for. Okay? So a very simple rule is a to the m over a to the n is a to the m minus n. Nothing more than that. Again, we add, we multiply, we kind of just put it on there, but that sometimes involves multiplication. Same thing here, and then we subtract. That's really all there is to it. Okay? Very simple calculation embedded in a more complex scenario. Let's look at a couple more like this. How about something like something like that? Okay? Now, what I always tell my students is the first thing you want to do is lay everything out. That means get rid of the parentheses that are in the problem. In order to get rid of the parentheses in this case, we're going to want to take those outward exponents and put them on to the inner pieces of the problem. Okay? So, what that looks like is then an x to the 8th, y to the 12th. There's 2 times 4, 3 times 4. And then an x cubed and a y cubed. Okay? That's pretty much it. Now, we can show the subtraction like we had here, okay? However, what I'm going to show you in a couple minutes can get a little crazy if you do it that way, okay? So instead, what I like to think of is you have x's that are going to be doing battle with each other, okay? We've got 8 versus 3. 8 versus 3, 3 will lose. And then we've got 3 will lose, but they're going to take someone with them. So there's going to be 5 up there. Okay? I'm still subtracting, but in a way that will always end up nice for me. What I mean by nice is positive, okay? When it's negative, I'll show you how to handle that in a couple of minutes. So again, 12 versus 3, 3 is going to lose. 3 are gone, so 9 are left. Okay? So what I'm left with is an x to the 5th, y to the 9th. There we go. Okay? Now, when I'm doing that subtraction, a couple of specific circumstances can come up. Okay? Here, I was subtracting, I got a positive, no big deal. What happens if I get nothing? Okay? What happens if I have something like this? Let's say we have y to the 3rd over y to the 3rd. Okay? If I do it just by doing subtraction, then I would have y to the 3 minus 3, which is y to the 0. Okay, no big deal. However, that's not simplified because what does that mean? You're multiplying y by itself 0 times. So let's explore this a little bit more. If I take this y cubed and over y cubed, just think of it in a general sense. I have something divided by itself. that always will give you a 1. Now, what I just saw is doing the same problem using two different methods. These results should be the same. So that means that y to the 0 equals 1. More generally put, anything to the 0 is 1. Anything to the 0 power is going to be a 1. If I give you something like this, what am I going to get? That's it. Because all of this mess is raised to the 0 power 1. End of story. Okay? Now, when you have to be careful is when there's multiple bases involved. What do I mean by that? Let's say I have that. A lot of people see that 0 and boom, they go to a 1. The problem with that is what's raised to the 0? Just a y. So when we're looking at this, y to the 0, yes, that's a 1, but we still have that 3. 3 times 1 is a 3, and there you go. So be careful with that 0. It is a very easy thing. You write a 1 and you're done, but make sure you're only replacing the stuff that the 0 was attached to. Okay, nothing more than that. Okay, now what about our other outcome? We could subtract and get a positive. We could subtract and get a 0. What about a negative? How does that look? Let's say we have x to the third over x to the fifth. Okay? If we just go with the standard rule of I subtract, it's always numerator exponent minus denominator exponent, and that would give me a -2. Okay? If you're taking notes, please write this down. Okay? If you're not, then just remember it. Never leave a negative exponent unless you're dealing with scientific notation. Never leave a negative exponent unless you're dealing with scientific notation. We'll talk about scientific notation in a few minutes here, okay? In that situation, the negative means something. It's needed for the notation. But in general, that's not considered simplified if you leave the negative in there, okay? So I can't leave that. So let's approach this problem a little differently. Again, when in doubt, expand it out. Three x's on top, 5 x's on the bottom. What do? We cross off those pairs of x's. Now what are we left with? An empty numerator, so just a 1, and then a denominator, that's an x squared. Now again, same problem, two different approaches, means their outcomes have to be the same. Okay? So what did we do? X to the -2nd, can always make it a fraction. We took this and flipped it. Okay? And when we made that flip, notice the exponent's not negative anymore. So what we're doing is taking the reciprocal. So what does that rule look like? Let me write it over here in blue so you can see it. Let's say we have a to the -m. All that means is you are going to take the reciprocal and change it to a positive exponent. Okay? It can go the other way as well. What if you start with that negative exponent in the denominator? Then I could just pull it up and turn it positive. Okay? So whether the negative's on the bottom, you pull it up. If it's on the top, you pull it down. End of story. Okay? Let's look at some examples. This pretty much concludes all the exponent rules that we need to know. Please don't look at this as just some mindless thing you need to memorize. A to the m times a to the n is a to the m plus n. Make sense of it. If I'm multiplying the same base, I add the exponents. If I have a power and then another power, I multiply those exponents. That's what I want you to get out of these rules. Okay? Now, let's pull all these together and look at more complicated scenarios. Let's say we have that. Okay? In a situation like this, okay, I already said in a previous problem, always first lay everything out. Get rid of the parentheses. There's no parentheses here. It's already laid out for us. The next thing I want you to do is change any negative exponents to positive exponents. Now remember, how do we do that? We flip the fractions. Okay? Now that doesn't mean we flip the whole thing. Just flip those bases that have the negative exponents on them. So that means this is going to go down and this is going to go up. Okay? So how does that look after we make that switch? The numerator doesn't have this anymore, so it has the y squared still. And then I brought up the y cubed, and it still has that z. Okay, so again, one more time. I still have this. I brought this up, and notice it's not negative anymore, and it still had that z. Then I had that x to the fourth, but also now x cubed and a z squared. The key to this is you shouldn't have lost anything. Everything should still be there, but maybe on another side. Okay, so this negative is now down here. This is still here. This is still here. This is still here. This is now up here. And this is still here. That's it. All I did was get rid of any negative exponents. And now anything that's still on opposite sides can do battle. So when I'm looking at this, the y's, I'm not going to reduce those. I'm going to join forces with them because they're on the same side. So I have a y to the fifth. I add those exponents. Okay? The x's, again, they're on the same side. So I get x to the seventh. Now what about those z's? Okay? They're on opposite sides. They're going to be doing battle. So I could take 1 minus 2, but then I get a negative. If I get a negative, then I got to flip-flop the fraction again. Let's avoid that. Instead, I have 1 versus 2. Who's going to lose? 1 should lose. But how many are left after they take someone with them? Just 1. So that z, there's still 1 in the bottom. And there we go. Okay? If you don't want to put that 1 there, you don't have to, but it's not hurting anything if you like keeping track of all that. And there's your final answer. Okay? So, let's look at a couple more. Okay. So again, it's all laid out for us, but we have a lot of negative exponents. So everything that has a negative exponent, flip it. Okay? I see a lot of people wanting to calculate this right away. Please avoid that because you're not going to be calculating with sixes. Okay? Because there's some fractions hidden in there. So instead, only work with the numerical bases once the exponents are positive. So what I'm going to do, let's go one at a time. This is negative, so I'm going to change it to the bottom, make it positive. This is negative, so I'm going to bring that to the bottom. This is negative, so I'm going to bring it to the bottom. Okay? This is negative, so I'm going to bring it up top. This is positive, so I'm going to leave it where it is. And this is negative, so I bring it up top. Notice again, I didn't lose anything. I just moved things around a little bit. Okay, so now I have to reduce all that. The 6's do not need to be calculated out. Okay, the 6's, since they're the same, will work the same way that x's and y's and z's would. So I have 3 versus 2. 2 are gone, 1's left. Okay, I didn't have to calculate that out at all. Over with the x's, they're on the same side, so I'll just pull those together. But the y's, 9 versus 7, 7 will lose. 9 take away the 7 will give me 2. Okay, now what's left? In that numerator, I have 6y squared. In the denominator, I have x to the 4th and x cubed. Don't write them separately. You've got x to the 7th. And there we go. I didn't really do anything crazy. All I did was flip-flop the sides of the negative exponent terms. I then did that, doing battle, top versus bottom thing. But beyond that, that's it. And when I was doing the battle stuff, it was just subtracting. Okay? So don't overthink this, but make sure you're writing this clearly. Don't cross things off just as a big mess, because you don't know what's there and what's not. Be very clear on how you're writing things. Okay? And then it'll be a piece of cake. Let's do one more. Okay, so you could reduce these a little bit with the top versus bottom and then apply this, or you can apply that first. I personally like to apply that first. Now, this cube has to go on everything that is inside those parentheses. Has to go on the x, the y, this x, and that -3. Don't forget about that numerical coefficient, okay? So, let's see how that's going to look. We are going to have -3 cubed. Never leave those parentheses off. Sometimes it's not going to matter, but if it matters, you need them, okay? So just put them there. If you don't need them, it's not going to hurt anything. And then I have x to the 4th, and then I cube y cubed over x squared cubed y to the -2nd, cubed. If you wanted to just go ahead and multiply those right away, you could, okay? Now, let's play this out. Now, this -3 cubed, if it was a negative exponent, I wouldn't calculate that out until I change the negative. But since it's positive, I don't really have to mess with it. I can just say -3 cubed is -27, okay? So I have -27 x to the 12th y cubed over x to the 6th y to the -6th, okay? Now, I laid it all out. What I then have to fix are any negative exponents. Now remember, I said negative exponents. -27 is just a regular -27. Leave that where it is. But this needs to switch sides, okay? So, I have -27 x to the 12th y cubed y to the 6th. Then x to the 6th, and that's it, okay? I didn't lose anything, I just moved that y up, and now I can start cleaning up. The only thing that's going to be doing battle are those x's. 6 will lose, 6 are left, because 12 minus the 6 gives you that 6, okay? And then, all together, I have -27 x to the 6th, y to the 9th. I get the 9th because I combine these by adding the exponents. If you want to put a 1 under it, that's fine. Not necessary, though. I would suggest getting out of that habit, but if right now it helps you by seeing that denominator, go right ahead. Okay? And there you go. Okay? So that's pretty much it for the exponent rules that we're going to be dealing with. Again, we're adding, we're multiplying, we're subtracting. That's it. We just need to pay attention to what we're doing and when. Okay? Also, please be very careful. Good bookkeeping. Make sure you're writing this as neatly as possible. Make it a little bit bigger if you need to. Notice I cross the entire thing here, or I just cross off that exponent, whatever it needs to be done. Okay? Beyond that, very, very simple, very straightforward. Just trust yourself. Okay? Now, the last bit of this discussion I want to throw in here is scientific notation. Let's define it first, and then we're going to do a couple quick calculations with it. Now, whenever you hear of any kind of notation, all that is a way of writing something. Nothing more than that. It's not some deep mathematical discovery, of something that existed forever. It's something that someone invented. Okay? So, when we're dealing with scientific notation, it is a way of writing values that are either really big or really small, okay? If we're dealing with, let's say, distance between planets, and we have to deal with this number, and honestly, that's not even that big, okay? But let's say we're dealing with that number, and we need to calculate with that number 20 times. Okay, that's going to be a pain in the butt, because of all those zeros that we're just going to keep copying and copying. Scientific notation allows us to shorthand this type of a value. Okay, same thing if we're dealing with in a biology class and we're dealing with a very, very small, let's say, size of a cell. I don't want to have to keep copying all those zeros. Okay, not only is it a pain, but also it's very easy to make a mistake, because do I have 10 zeros? Do I have 11 zeros? You got to be careful with that. Okay, so again, what this allows us to do is shorthand that. Let's see what it looks like. In general, scientific notation looks like this. That x that's in the middle means multiply. Okay, you are multiplying a number times a power of 10. Okay, our number system is base 10. So what that does is it counts decimal places within the number. Now, the a value has to be between 1 and 10. Now notice how I wrote that. It could be bigger than or equal to 1, but it has to strictly be less than 10. Okay, that's very, very important. Be very careful on that. So basically we want a ones digit. We can't have a tens, hundreds, or anything beyond that. The n. N is an integer. Now, when I introduced negative exponents a couple minutes ago, I said never leave negative exponents except with scientific notation, because a negative exponent means something. An integer, remember, is going to be one of those values there. A solid number, no fractions or decimals, but it could be positive, negative, or zero. Okay? Now, let's start just converting some numbers back and forth, and then we'll finish up with those calculations. Let's say I want to go from standard notation to scientific notation. Okay, again, these examples are not really going to be examples that this was made for. I'm going to keep, the numbers are going to be a little bit more manageable just to illustrate the idea. Okay, so let's say I have something like this. You'll find those commas are very, very helpful. Every 3 digits, put that comma to help you keep track. Okay, so what we have is what? 3,410,000,000. Okay, if I don't want to write that again and again, this is what we do. Remember, if there's no decimal in a number, the decimal is understood to be all the way on the right side. Okay, What we're going to do is move that decimal back so we end up with a number that's between 1 and 10. So I'm going to start moving back. Okay, if I stopped here, I would be at 341, too big. 34.1, too big. 3.41, perfect. So I changed this to a 3.41. Now I can't just change it and that's it. I need to compensate for that move. Every move I made was a power of 10, a multiple of 10. So how many did I move? I moved 1, 2, 3, 4, 5, 6, 7, 8, 9. So I am going to say times 10 to the 9th. That's it. Okay? How about something like this? Now again, I need a number between 1 and 10. That's too small. So I need to move that decimal, which I can clearly see right here, back the other way so that I end up between 1 and 10. If I were to stop here, I'd be at 0.51. That's too small. But here, I have 5.1. That's perfect. Okay? And then I'm going to multiply by a power of 10. How many spots did I move? 1, 2, 3, 4, 5, 6. But this is different. Now I'm going from something smaller up to a 5.1. So again, I moved 1, 2, 3, 4, 5, 6. I'm going to say -6. Okay? Now, what I see a lot of students do is they want to say, well, if I moved it to the left, it's positive. If I move to the right, it's negative. Here's the problem with that. When we do the other way, I'm going to show you that in a second, then you got to switch those rules. Okay? I like to phrase this in a way that works no matter which direction you're going. Okay? I always think of the normal standard number. The standard number is bigger than this scientific number, therefore positive. Bigger, positive. This standard number is smaller than the scientific number. Smaller, I associate with negative. Let's see it going the other way. Let's say I want to go scientific to standard. And let's say I have a 2.89 times 10 to the negative fourth. Okay? Now, I'm going to take this scientific version of the number right here. And now I want the standard to be smaller or bigger. A negative means the standard should be smaller. So to make this smaller, I'm going to move it this way. 4 spots. And if I have blank spots, I fill those in with zeros. So what I end up with is a 0.000289. The zero in front is just to kind of accentuate that, hey, there's a decimal, be careful. If you don't put it, it doesn't change anything about it. Just make sure the decimal's clear. And that's it. Let's say we had 1.3 times 10 to the 8th. So I start with that scientific form of it, that 1.3. I know I got to move it 8 places, but which way? If this is positive, that means that normal standard version should be bigger. So to make this bigger, I got to go this way. 1, 2, 3, 4, 5, 6, 7, 8. And I fill in a bunch of zeros. Okay, so I have 130 million, and that's it. Okay, so again, it's a very easy thing to do. The number tells you how many spaces to move. You just got to pay attention to which direction. Nothing more than that. Okay, let's finish this up by talking about a couple of calculations using scientific notation. We're not going to be adding and subtracting these values typically. We're going to be looking at them in terms of multiplying and dividing. Okay, not that you can't add and subtract with them, but the real usefulness of these come in when we multiply and divide. Okay, so let's say I want you to write the answer in scientific notation. Sometimes the book has you go to standard notation. To me, if you're using scientific notation, the point of it is to use it. Okay, so that's why I usually keep this in scientific. Let's say I have 8 times 10 to the third over 2 times 10 to the negative fifth. Okay? Now, when I'm dividing like this, I'm going to be dividing like pieces. You have this numerical, just the regular number in front, then you have this power of 10. Those powers of 10 have the same base. So, what is 8 divided by 2? 4. No big deal. But then I have a power of 10 to deal with. Now, before I would say, okay, top versus bottom, who's going to win, who's going to lose. In this case, the whole point of that was so that we avoided a negative exponent. We don't need to avoid it here. So I would just go back to the basic idea of we're subtracting. So in order to divide these, I would take the 3 minus negative 5, which turns into 3 plus 5, or 8. And I would leave it as that. Again, the book may have you then convert it to 4 with 8 zeros at the end. To me, that kind of defeats the purpose. Okay, but this is what I would personally be looking for. Okay, how about multiplication? Let's say we have 3 times 10 to the negative 11th times 2 times 10 squared. Let's say 4, just so we don't have a bunch of 2's around. Okay, here we divided 8 divided by 2. In this case, what's 3 times 2? We're multiplying, right? So 3 times 2 is 6. We still have those powers of 10, the same base of 10. When we multiply those powers of 10, we're adding the exponents. So that's a negative 7. Done. End of story. Negative 11 plus 4 is negative 7. Now, what happens when it doesn't work out so nice? Let me show you what I mean by that. Let's say we had 7 times 10 to the 5th times 3 times 10 to the negative 7th. Okay? You think, oh, piece of cake. 7 times 3, 21. That's a problem. Because remember, scientific notation requires a number to be between 1 and 10. That's too big. So what I like to do is I like to hold for a second. Stop right here. Don't deal with these powers of 10 just yet. Focus on this 21. Okay, again, 7 times 3 is 21. That needs to be between 1 and 10. So convert that. Let's say I say 21 is your standard number. Get it into scientific notation. Decimals here, and I bring it back 1 spot. That turns it into a 2.1 times 10. I know it's going to be to the first because I moved it 1 spot, but is it positive or negative? Okay. Now you could think, okay, the standard 21 is bigger than the scientific 2.1. Bigger would mean positive. Or think about it, guys. What's 10 to the first? That's just a 10, right? What's 2.1 times 10? 2.1 times 10 gives you the 21. So this isn't just some funky notation. You're multiplying by 10. That's all there is to it. Now, from here, now that this number's in a good spot, I can then pull these down. Okay, again, I'm multiplying, so I add the exponents to get that negative 2. 5 plus negative 7 is the negative 2. Okay, but we're not done, because now we have 2 powers of 10. That's not okay. So let's pull that together. 1 plus negative 2 is negative 1. And there we go. Okay? It's okay if you have to watch this a few times, okay? Because you want to pay attention to where all the mechanics are leading us. Multiply to get that number. It's too big. So I convert it back. There's your scientific notation. Let me use a different color. This is broken into that. Okay, and then these 10s come down as this. Pull it together, we're good to go. Okay, let's go to this next one. Not this one. Put a new problem on the board. Let's say you have let's say 9, not 9. Let's say 6 times 10 to the negative 11th over, I'm sorry, let's say 3 here and then a 6 here, times 10 to the negative 23rd. Let's say that. Okay? Now, again, right off the bat, piece of cake. I just divide. 3 divided by 6. Normally I would say 1/2, but we're dealing with scientific notation. Fractions don't really apply too well to scientific notation. Write it as a decimal. 6 divided by 3 is a 0.5. Okay? Just like you would never say, you know, I have 7/11 dollars. You put that as a decimal, okay? Or 3/4 of a dollar. You say 0.75. Same thing here. Don't write it as a fraction, write it as a decimal. Now, is that okay? No, it's too small. So I need to make that bigger. So what I'm going to do is I'm going to bring this back 1 to make it a nice clean 5. That's between 1 and 10. Now I multiply by 10 to the first because I moved it 1 spot. Now, should I leave it positive or turn it negative? Think about it. If I leave this positive, that's a 10. 10 to the first is 10. 5 times 10 is 50, not 0.5. So it has to be a negative. Again, if you want to just think, well, this is smaller, so smaller means negative, that's fine. But if you're not sure, just think about the multiplication. Okay? If one doesn't work, then it has to be the other. Then so right now, this all is the same thing. At this point, I can then pull these 10s together. Remember, I subtract. So I have a negative 11 minus negative 23. So I'm really adding. Okay, and what I get is a positive 12. Okay, now don't stop there. I still need to pull these 10 powers of 10 together. So I have a 5 times 10, negative 1 plus 12 is 11. And there we go. Okay. Again, don't be afraid. Don't be upset if you have to watch this 3 or 4 times. Okay, but watch it so you can see the mechanics of this. This shows you why we have the scientific notation. So I don't have to deal with all those zeros, and it makes the calculations a lot easier to deal with. Okay, and just the regular multiplication and division, let alone all the other decimal movements and all that stuff. Okay, so as always, work hard. Let me know if you have any questions, and I'll see you next time.